Hey everyone, welcome back. We are learning about semiconductors. In the previous lessons, we saw how to reverse bias a diode, and we also saw some types of diodes such as p-n junction diode, a Zener diode, and a Schottky diode. In this lesson, I'm going to walk you through some more examples of two-terminal semiconductor devices. First is the tunnel diode. Tunnel diode is also called as the Esaki diode. Now this is a symbol of a tunnel diode. This is the cathode and the anode. Do you remember the symbol of the p-n junction diode? We just had a straight line at the cathode. Now here we have something like a bracket. It symbolically represents a tunnel. Now a tunnel diode operates in negative resistance. There's something called as a concept of tunneling. In a tunnel diode, both the p and the n junctions are heavily doped, about 10 nanometers. Now this is how a tunnel diode looks like. Now what happens when we forward bias a tunnel diode? Because p and n junctions both are heavily doped, the depletion region is very small, and so the electrons tries to tunnel through a very narrow junction. The electron fills the states of the conduction band in the n region and starts to align with the holes in the valence band of the p region. And it operates in negative differential resistance. Now what does this statement mean? This means that even when we increase the voltage, the energy is gained by the electrons and it tries to tunnel through the narrow junction that's present due to heavily doped p and n junctions. So although we increase the voltage, the conduction drops, and that is what is meant by negative differential resistance. Now this is a diagrammatic flowchart of what happens in a tunnel diode. When we increase the voltage, as we saw above, there's going to be a drop in conductivity. Now due to this conductivity drop, it causes misalignment of the energy states with one another. When the energy states start to misalign with each other, the electrons travel through normal conduction and there's no more tunneling effect. So a tunnel diode starts to act more like a normal diode, where it conducts electricity through flow of electrons and not tunneling effect. Now what happens when we reverse bias a tunnel diode? It's called as a back diode. Here the fill states on the p side and starts increasingly getting aligned with that on the n side. Here the electrons flow or tunnel through in the reverse direction, causing conduction of current. They are used as fast rectifiers even at zero offset voltage. Rectifiers are those that can rectify the signal from AC to DC or vice versa. Where are these tunnel diodes being used? We know that they operate in a negative differential resistance, and because of this character, they are used as oscillators and amplifiers. Amplifiers are those that are used to amplify or increase the signal. They are also used for switching circuits using hysteresis. They also have low capacitance. Capacitance is the ability to store charge. And because they have low capacitance, they are used in microwave frequencies above all the ranges of any ordinary diode or a resistor. There are also many types of tunnel diodes such as a resonant tunneling diode, a metal insulator metal diode, a metal insulator insulator metal diode. All these help in step tunneling effect, that is, you could tunnel in 2 layers or 3 layers or more. This is used for precise control on the diodes. Moving on, let's see photodiode. Some of them confuse between a photodiode and a light-emitting diode. There's a big difference. A photodiode senses light and converts light into electric current, but a light-emitting diode emits light when current flows through it. So a photodiode, it converts light into electric current. Now the photons are being absorbed. And one factor is that more the surface area, more the light that's being absorbed, and the response time is very small when the surface area is more. This photodiode is designed especially to operate in a reverse bias. Now this is a symbol of photodiode. Now we have the arrow mark coming in, representing that light is being absorbed by the anode. Now, where is this photons being absorbed? They're absorbed by the carriers that are present in the depletion regions. The carriers are swept by the built-in electric effect in the depletion region, and due to this, the holes start moving towards the anode and the electrons move towards the cathode. And we know that photodiode is designed to operate in reverse bias direction. So what happens in a reverse bias? The opposite terminals are connected, and so the charge carriers of opposite charges tend to be accumulated at the end of the diode, and so the depletion region width increases. And so we can also tell that the current that is emitted by the photodiode is the sum of the dark current and the photocurrent. Dark current is the current that is produced by the photodiode in the absence of light, whereas photocurrent is the current that is produced in the presence of light. Now this is more like a flowchart or a diagram representing what happens in a photodiode. We saw that photodiode acts in reverse bias. So in reverse bias we know that there is an increase in the depletion layer. And so when the depletion layer increases, what happens is the surface area increases. So it has more surface area where it can absorb more photons. So when more photons are being absorbed, there's a very little response time of current being emitted back. So when there's very little response time, the ability to store charge is less. So that is what this statement means. There is a decrease in the junction capacitance, where capacitance is the ability to store charge. And so the dark current also increases without much change in the photocurrent. Finally, let's also look into light-emitting diode. A light-emitting diode is just opposite to a photodiode. Here, when current flows through the diode emits light. Here the electrons recombine with the holes and energies are being released in the form of photons. Now this process is called as electroluminescence. Can you think of some LEDs that you daily see every day? For example, the headlights of car or traffic signals and a lot more. Now this is a symbol of a light-emitting diode. This is the cathode, this is the anode, and we have arrow marks going outwards. Now this represents that light is being emitted out. Now, do you remember the symbol that we saw in photodiode? The arrow mark was pointing inwards, showing that photons are being absorbed and current is being produced. So now, you might have a doubt that, come on, there's so much of color lights that are being emitted. How does different colors come out? So, the color that is being emitted by the LED depends upon the energy that's required for the electron to cross the band gap. Now say, the energy required for the electron to be excited and jump to conduction band is X. Then the corresponding light having a wavelength of X is emitted out. Now if we need white light to be emitted, then we can use multiple semiconductors or a layer of light-emitting phosphor over our semiconductor device. Now take a look at this picture. This is how an LED looks like. Now let me zoom in for you for a better or clear understanding. Now we have a semiconductor over here, we have a wire bond, and we have a lead frame for protection, and this acts as a cathode, and this is the anode, and this outer cover, which is the epoxy lens case, is for protection from external environment, stress, or any other external factors. So yeah, we've come to the end of this lesson. Long story short, in this lesson, we learnt about three types of the two-terminal diodes, that is, LED, photodiode, and a tunnel diode. There are actually more types of two-terminal diodes, but these are the most common ones. In the next lesson, we will be learning about three-terminal semiconductor devices in which it can conduct electricity through three terminals. Well, thank you for watching and stay tuned for more. If you have any queries, please ask me in the comment section below. If you liked the video, please like it and share it with your friends.